It is normal. It is normal.
Yeah.
You'll see November.
Okay.
This is October. You'll see November. Machine. Publish the video. We'll be back here. Needed. The source is not needed. This is, come on, I'm saying. Yeah. Should we wait someone else? No. So, let's go. I have something new for today. It's old but new. Today, I would like to speak about load regimes. It's one important thing. Yeah, everything works. Yeah, this is fine. This point causes problem, usually, with understanding. So, I will spend some time to illustrate an idea of load regimes. To illustrate it, I will use one quite old device. It's called rotating field model. It was made by Tinsel company. It's approximately 100 years old, but it still works. This device has movable coil and two static coils. Idea: static coil number 1, A, B, and something like this. It's a static coil C. Number 2. Two static coils. Device is powered from two voltages. This is A, B, it's voltage 1, and this point comes to, this is C and this is D. This is voltage put. No second voltage. Angle between voltage is 90 degrees. I got it. One is from my transformer. One is A0 and second is a part of linear voltage BC. So I got 90 degrees between two voltage. Device is called old. It's from the time where two-phase networks existed. Maybe you don't know, but first Niagara project was two-phase, not three. Still, now can be found in the United States 4-wire networks for two-phase. Okay, these are static coils. I also can use a movable rotating coil. It has to output, it's a rotating coil. As I draw it now, this coil has a magnetic coupling with the first static coil and near zero with the second. What will be the output voltage of this movable coil? It will be like this. If I rotate it in the, let's say it will be like I'm drawing in orange, if I rotate it to 90 degrees, what will be output? I can rotate it and get, I can get this voltage like this, like this. I can have any direction of the output voltage of this coil just by turning the handle. So I can come closer. I can come closer to my experiment. Here it is. Here it is my rotating field model. So I can get any desired angle of the voltage. Now, what you see? I'll put the power. I have three lines on my scope, yeah? Yellow, blue, and red. The yellow line is a network voltage, simple voltage. The blue line is current, and current circuit is powered from my rotating field model. I can get any angle for my current. Here I can simulate any desired regime, or more as you want. So, with the twist, like this, to make model visible, I can get any angle between voltage and current. What kind of regime do we see now? What can you say? What's the angle between voltage and current? Any idea? This way, it's more pretty. This way is better. Like this. I think this is okay. So, what's the angle between voltage and current?
Maybe 90 above 90 or 100 or 110 or below.
Angle between blue and yellow line.
Blue and yellow, yes.
Between blue and yellow. Yellow is voltage, blue current. So what's the angle? 0.
Oh, it's not a 0.
It's near 0.
Nearby 0, but it's
No,
not exactly.
it's okay, I can.
Because the machine showing error.
There is a. I can make it more precise.
Yes, it's not a 0.
There is a bit error. My instrument shows this is near 0. What kind of load do we see if it would be a load? We have load powered from AC network. What kind of load should it be?
Voltage?
Load.
Watts.
Yeah, load. But what kind? Active, resistance, coil, capacitor.
Maybe active.
What means 0 shift between voltage and current? No energy is stored. No inertia. No inertia means what the load is pure active. Yeah? It's pure resistance without any inertia, without any energy storage. Okay. Let's do, what can we do? What's the angle now?
See?
Really? Do you think there is no angular shift between these two lines?
No,
Really?
realistically, maybe 90 degree.
90 degree and leading or lagging?
90 degree lagging.
Really? What's the time direction here? Time goes from there to, this is the time direction. What comes first? Current or voltage?
The current, yes. It's
Current first is mean what kind of load I'm simulating? When the current comes in front of voltage? Huh? Come on. Battery of what I'm holding? What's the name of this device? Capacitor. It's a battery of capacitor. In case of capacitor, we will see things like this. No, when I come back, here is my 0. Active load.
Active.
Who's calling me? Active load. Active load. +1. If voltage is real, current, okay, I need to draw yellow voltage. Here is the current. Do you agree? What this pair of sign can be projection of these vectors to imaginary.
Yes, yes.
if we rotate them with the omega speed. Now, what? Here is voltage, 100 volts, and here is current, 0.9 amps. Now, what about power? You see, the red line is an instant power. What will be if we integrate from 0 to period multiplied? What's the meaning of this mass formula? Energy supplied to load from one period. If this is a 0 time, one period is 20 milliseconds. 2 divisions. From here to here. We need to sum all this. It will, in fact, energy supplied to load will be area of this figure. Understand? You see what all positive?
Yes,
This means what all this multiplication goes to load. Come on, power factor. Power factor is 1. And I have 2 instruments here. I think you see it in the first time in your life. One measuring watts, and second one measures reactive energy.
Which instrument measures the power factor?
This one, power factor.
Oh, okay. And the angle?
And this one shows angle relatively. It has a 0 point here.
Okay.
Up. I can put it.
Okay, I understand.
One is here. You see there are 2 directions. It's a rare thing. They are quite rare because they have 0 at the center. For this case, in the power coordinate, we will see this with C0. Here, between an angle, T is 0. Pure active load. That's what we will see if you put an incandescent, old incandescent lamp. You'll see something like this. Let's go change something. See, current is lagging. I'm adding a phase shift. Watch the power factor. 0.6, 0.5. See what happens? Active load, all power goes as active. 0 reactive. Current is lagging. What I'm doing? I'm adding what kind? Capacitive or inductive? Watch, power factor going to 0. Current lagging?
Yes.
Yes. Now I'm creating +1. Voltage, current now, leading by 90 degrees. You see?
Yes.
what will be sum of energy if you take it take within one period? What will be sum of energy? Plus energy goes into load, minus what happens? Energy from load returns. What kind of load now I'm simulating? If we have pure 90-degree shift. When current is lagging by 90 degrees from the voltage. Silence. Coil. They are not respecting you. It's a coil. Coil can store energy in its magnetic field. Coil has inertia. Inertia slows the current. So current is lagging relative to voltage. You see it? What happens? At this moment, energy goes to coil magnetized. Next moment, what happens?
Discharge.
Coil discharges into network. And now coil magnetizes, demagnetizes, and so on. What will be sum within one period? What's the area of this figure? Real.
In real.
Positive.
In real is 0.
Yeah. In reality, we will get, integrate this figure, we will get 0. Its energy just wobbles around, giving nothing to load. Look here, active power, 0. Reactive, it's a 15 division, should be multiplied by 5. It's a 75
yes.
watts. But not watts, but volt ampere reactive. Voltage the same, current the same, but power factor is 0 and active load, amount of energy spent in load, usable energy is 0. This is situation. It's like this. Pure cool. Like up 90 degrees. P 0 cool. In my case, okay, 75 volt ampere. In previous, is 0 power factor. In reality, you'll see something very typical. Figure, for example, this motor has a design, manufacturer says, but under nominal load, it will have power factor 0.83. So this is very typical, about 0.8, 0.85, something like this, 0.85. This is very typical for the industrial kind of load. Somewhere between 0.8 and 0.9. We have a power factor phase shift. You can see it will be 73 active watts, and here I have 5 division and 25 active. we can do what we can do. We can reduce losses because reactive component, draw it in yellow, something like this, we'll see, and no, like this, wrong, I need something like this, and something like this for power factor 0.9. We can compensate reactive power by adding a capacitance in parallel to our load. It will reduce losses. Watch what happens if I add capacitance. See, now power factor. It's a good compensation to 1. In case overcompensation. Now current is leading relatable to voltage. You see it? I will put it to the limit. Here, power factor is 0. You note what current model didn't change. I changed only angle. And what we got? It's a limit point, 0 watts. You can see energy just wobbles around. It's like charging capacitor and discharging capacitor without any usable, without any profit of this. And I have 1015 minus 75 volt ampere reactive. Here at the limit, I have regime mode like this. I have voltage and leading current. In that P, it will be like this. And here again, power factor is 0. But I have capacitive load. What I'll change from 0 capacity I'm going to power factor 1 and again here is the point. I should stand here. Here power factor 0 lagging, power factor 0 leading. Leading 0, 1 completely active load, pure active, and power factor 0, pure coil. In blue, capacitor, in what kind of color? In yellow, coil. an active resistance. This part is clear. I would like to go. Really? Oh, you sure? Well, this part is clear. In the power plane, we have these two quadrants. The same is when we speak current related current in relation to voltage. These two. But I have four. You see? What would you say about this? What's the angle between?
190.
Really? 180. They are in opposition. Voltage here, current in opposition. What's the regime? Ideas? Do we consume energy? Is it consumption?
Yes. No.
No.
It's
In opposite.
no.
We have a generator regime with power factor 1. Power in negative means we have a generator regime. This is what in mirror mode is a generator. I will add to my picture active power, reactive power. Active load this way will be coils, capacitors, ideal capacitor, ideal coil. Load regimes in opposition. Do I have some? Okay, it will be green. Minus, it's a generation regime. Now I have ideal generator without shift. You see what's in minus? We are not consuming, we are supplying. That's because mine.
No, we have.
One second, I want to. This regime. Switch to 0.6. even 30, yeah, 45 degrees. What kind of regime do I have now? Minus coil. It's kind of minus coil. Take a look. I can do like this. It's a border. 0 watts and 75 reactive. Capacitor. I'm going first. Active component increases, but with a minus sign. I'm supplying more and more active power. Here, 95 degrees. Minus coil. See, it's lagging, but it's a minus sign. At the present moment, come on, I'm here with the power factor minus 0.7. It's a minus coil regime. Regime minus Q. I'm supplying to network both active and reactive power. It's an overexcited regime of synchronous machine. What's the regime of synchronous machine? Can you answer me? Yeah, I'm talking to you. What's the regime of synchronous machine when we supply both active and reactive power to the network? Maybe your Facebook account can answer. Each real synchronous machine has source of its magnetic field. When we can control EF or excitement current, if current is, let's say, it's normal regime, we will supply pure active power. If we add this, let's say, more current, if we go beyond this point, we will see interesting thing. Our machine starts, if it works with the network, if it's alone, we will see just increasement of voltage. But when machine works in parallel with its network, it can change voltage of whole network. And it's mean what? Real EMF of the machine starts leading. And machine becomes a kind of huge capacitor. Overexcited synchronous machine supplies reactive power to the network. It's the way to control a network's voltage. If you overexcite your generator, voltage will rise. You see it as a flow of reactive power to the network. Now you see mode when machine supplies both active and reactive power to the network. I can go further. This is pure active load. No reactive power is supplied. You see, it's all in positive, but with all negative, because we are supplying here pure capacitance. Only reactive power is supplied. Power factor 1, only active power is supplied. Here are modes between. Minus P minus Q means we supply both active and reactive power. I can go further. Here it is. watch this regime. Minus P plus Q. Somewhere like here. Yeah, something like this. 10 on 10. Under excited synchronous machine. We have now a regime when active power goes from our power plant, but we consume reactive from the network. It is here. It is minus P plus Q modes, or minus capacitance. Mode when active power goes from us and reactive here. At night, here in Latvia, we have one problem. Capacitance of our 330 kilovolts network is quite large, but load, reactive load at the night is much smaller. And this means that we need to put somewhere reactive power generated by our high voltage line. We have one of the way near the rig, we have a door power plant. It's possible to switch any generator in the so-called synchronous compensation regime. It can rotate without any active load, even without any. It's possible to clear this spiral chamber with compressed air from water. It can run dry, or it can run with water and supply active power, but excitement system allows to set negative, let's say negative direction to, let's say, suck reactive power from the network. To prevent overvoltages, these generators are equipped with such excitement system, so it's normal for them to work in reactive power consumption or say diminishing mode as anti-capacitor. This mode, when active power positive, active power supplied is negative, sorry. For our reference point it will be negative. But reactive is positive. With supplying active to network and take reactive from the network. We see what's called 4-quadrant modes. So we can simulate any of the load regimes. I have one object. This is I'll put it in place of reactive power meter. One sees. This one goes here and It's a metal. Let's see what's happens. Power factor. Come on. Power factor. Yeah, power factor 1. Meter goes forward. No, it's a 2 tariff meter, old 2 tariff meter. When you over consume, it has also clock, and this part measures peak hour consumption. Yeah, it's an old 2 tariff meter. It also has a clock. When a pulse from clock comes, this thing starts counting over consumption, and this goes. This one goes forward and switch. No, it turns and inspection came. Okay, you consumed 100 within a peak hour. You find. How can I get? I would like to get both instruments and my meter visible. Okay, we can see. What's now? Ideal load. Power factor 1, 75 watts, 0.8. What kind of load is now? Power factor 0.7. Only half. You see? Speed. What is the change of the speed? Power factor 1. This one. Power factor 0.7. It's decreased by half, but current remains the same. Why? Because only half of energy comes to load. Another half wobbles. Is wait a second. This one. Power current falls.
It's moving, but very slowly backward. Yes, it's moving very slowly backward.
Yeah, one. Yeah, now it's still.
Yes, but the power is positive.
We need to check zero of the scope. No, power factor is 0 watts, 0. Current falls. We have ideal coil. Flow is 0. In opposite direction, here. Again, current flows, power 0. Power factor, leading. See? Weight is, for example, here, power factor 0.7, 45 degrees. We have active power, but only half. Current remains the same.
Yes.
We have, now it's mixed active and capacitor. Ideal capacitor. 0. Current falls, but no usable energy. But I can go -1 power factor. Pure generation, we are selling. We are not buying, we're selling. And you see, what? It goes in opposite direction. Happens. Yeah, goes in opposite direction. What's the mode? Minus capacitance. We consume reactive from the net, but supply active to the net. Goes forward. Here. 1/2. Zero. Yeah. Power factor -1. Current is same. Full speed, but with negative sign. Here it will be 1/2. Power factor 0.7. 1/2. And it's positive. What kind of mode should I get? This minus capacitance leads here will be 45 degrees. Negative. We supply active but consume reactive. No, active will be positive. Because my setup is at like load. What comes to us is positive. What comes from us is negative. Here you see it goes in opposite direction. Yeah, because active power is negative. Because I'm supplying I'm simulating. In real, it's only consumes. But with the help of my field model, I can simulate any network regime. On my goes back. Stand still. Current still full. Network stand still. Here power factor 1 goes forward at full speed. Opposite. Pure capacitor, pure active, pure coil, pure generation, minus coil, minus capacitor, this is minus coil, sorry. Coil with the minus, we supply reactive power. Minus capacitor or mirrored capacitor. We consume both active and reactive. Yes, it's complicated. Without knowledge of without knowledge of the vectorial system, you cannot. You see what voltage and current, neither voltage changes, neither current changes. The only thing that changes is an angle between current and voltage. And it changed a lot. And to count this, and the only real way is to or kill yourself with trigonometry or use a complex representation. Stands. Current flows, voltage, but it costs nothing. Current flow, voltage present, cost nothing. Same current, same voltage, you pay. Same current, same voltage, and theoretically you got paid. Your supply, they should pay. Theoretically. In theory. See what it works. Big rules. I'm concerned on power factor. Your inductive, your capacitance, here, power factor 0.7, loads by half, and 0.0, the sign here, -1, your generation. Not possible. You can do things like this. Minus coil. Or it's minus V. This point. Full speed. Okay, full speed forward. What kind of load? Kind. Yeah. Power is positive, but what kind of load do you see? Current is lagging or leading? This means what we are dealing with when current is lagging. I will meet you in nightmare. meet you in nightmare. It's a coil. Switchable. It's not the biggest one. This one is bigger. It's my giant coil. Coil. Yeah. Stands. Bit. You have bit active.
Yes, big active.
Small. You have increases. Overshoot. Power factor 1. No, it's over. The upper one. Small one is the service. This big cross is actual. See? Index shows power factor 1, but with minus sign. Here is the angle 0, and power factor by cosine is 1. 0.907 corresponds to 45 degrees. 1/2. Do not confuse coils with capacitors. It's a nice coil. It's for demo free energy. No? Forward. What regime did you set? It's 0. And what happens with reactive power? Behind the meter. 0? Active is 0, but reactive? Minus. You have power factor 0.
Yes. Little bit 0. It's not exact 0.
What kind of load you have now?
0 watts?
0 watts minus see red digits, and should be multiplied by 5. It's something like minus 75 watts. What kind of load do you have now? What's your simulate?
Multiply by 5?
Yeah. white? And be like Morpheus. Red or white?
White. White.
What comes first? Voltage or current?
The current is lagging, the voltage is
Really? Lagging? Serious?
No, it's leading, I think. It's not from the
Serious? What's first? Current or voltage?
the voltage.
Really? Voltage.
From here.
Zero.
The voltage is lagging, the current is leading.
Which way the time goes? To the right. Where you see thin red line, thin vertical line. It's a zero time for the scope. To the right is past, it's history to the right. Now, for the scope, now is where the thin line. Who arrives first? Current or voltage, blue or yellow? Blue. This means what? Voltage lagging, current leading.
Yes.
When current leads? When voltage lagging? You have only two choices. Coil or capacitor? Capacitance. So, what kind of load do you have? You have 0 watts. You have minus 70 watts. 0 watts means that there is no resistance.
Yes.
Current leading, so you have a capacitor attached.
Yes.
Oh, it's overexcited synchronous machine with no mechanical torque. If we have a synchronous machine, can you supply us some active power?
Okay.
You have watts and watts. You have active and reactive. So what we got? What's now? Where are you?
Very high.
You can obtain any region. And what you got now? Okay, let's look on this one.
Okay.
What's the angle between voltage and current? You see what? Which way matter rotates?
The voltage is 90.
If matter goes in negative direction, see, it's negative. Are you supplying energy or consuming? Supplying. If you're supplying, this means what angle is over 90 or before or less than 90 degrees?
Maybe mechanically it's a 90 degree.
No. It's 90 degree corresponds to 0 in active power. Are over 90 or less than 90?
I think over 90.
Over 90.
Yes.
It's simple because 90 is a horizontal line on power factor. You have 90 plus, okay, it was 90 plus some 45. Here you have 180, 9 pure active. And before it was?
Only the current only negative.
Okay. Current is leading or lagging to 180 degrees. It's the same. There is no difference. You have power factor -1, so current is opposite to the voltage.
Why the voltage is low?
Because it's made.
Okay.
You're only changing angle.
Yeah. It's 90 degree, but now also the current is leading.
Yeah, current is leading. 90 degree, power factor 0, active power 0, and reactive -7.576, something like this. Get us positive reactive power.
Positive reactive power.
Positive reactive power. No.
Okay, it's positive.
No. It's reactive power is positive.
Yes, but you need to reactive power is negative.
Do you think now reactive power is positive? It's something.
No, active power is positive.
I'm asking for reactive. Get us plus P plus Q. What kind of elements corresponds to plus P plus Q?
Now the active is positive.
When we will get positive active and positive reactive? What do we need? If we would like to get both positive.
When the current is lagging.
Yeah, we would like to see lagging current.
Yes.
But what do we need? What kind of load it can be?
It's
If both.
what is I think 0.
No. What kind of elements we have? We have capacitors, we have coils, and I'll put active resistance here. And active resistance. If you see positive P and positive Q, this means what should we connect?
Positive Q
And positive P.
Maybe capacitors.
Really?
Positive 2 and positive Q.
Positive P, positive active power, and positive reactive power.
Okay, maybe
Both positive. What should they connect?
Inductance.
Yes, one.
Just, leading the.
It will be positive Q.
Yes.
And how we will get positive P?
It's a resistor.
Yeah, it's a resistance. So what will have active component, resistance, and reactive.
Yes.
For example, this one too big, smaller motor can be. Simple asynchronous motor will be plus P plus Q. Plus P because it carries real mechanical load, and we need something, we need to magnetize with some energy its magnetic system. Okay, and if we would see minus P and it was minus P minus Q, okay?
Minus P minus Q. It's I think minus P and minus Q capacitance plus minus Q.
Minus Q capacitance, okay?
Minus P is a resistance maybe. Because
resistance consumes energy.
Okay, maybe it's stored energy. Inductance.
Not to supply energy, we need a source of energy. It should be generator.
Okay.
Someone should rotate. I need to bring a generator. Generator. Nothing here. No. Not so easy. Nothing is easy here. My nice capacitor. Nice. I don't want to disassemble my network. So because of my resistance. At the second meter. For quadrant beam. It's very strange for me, but this even high skilled guys confuse negative modes. I don't know why. Come on, man.
Yeah, it's fine. We need to activate the Linux backend. Otherwise, the hardware is good. Because I only installed IR. So that's why I told you. Because everything is new. It's Malayalam, Tamil. Both are similar, but since still we are serving each other. Yes.
1, 2, 3, 4. 1, 2, 3, 4. Not forget to feel the attendance. Please. It's okay. What I'm doing. Oh, what should I do? Strange. We have 2 viewers online. Where should we go? Where should we go? I just want to disassemble network. So it's the same but in bit different notation. More methods of the god of methods. More methods for the god of methods. Here and the right one will go here. I will put them in the column. No. No, 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 no. Okay. Wrong direction. This one should go to this one. And this one should go here. Now, next one. This is, yeah, it looks like it will be voltage from, but it's I'm not making a mistake. This one goes here and 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 last line. There always situation when you need one more one. You always need one more. It should go three. Wait. No. It should go here. And somewhere. Let's take a look. Not good. Not good. Not good because this one should go here and this one should go here. Yeah. I have created a bit closer, a bit strange network. I have used my second meter, but this meter gets same current with the whole network.
Yes.
But voltage, remember, when I start speaking about my model, it takes 2 voltage, receives 2 voltage with a 90-degree shift. I have powered the voltage coil of my second meter from the second voltage. Now it has 90-degree shift relative to the current. Now, if you can see, I'm simulating a cosine phi 1 mode. Power factor now is 1. That means what active energy flows, and you can see the first method rotates, and reactive energy stands still.
Yes.
Now let's simulate what? What I'm simulating? What kind of mode? Lagging or leading? Lagging.
Yes.
90-degree angle, power factor 0. 0 active power, and you see reactive power meter. Now it's reactive. It's running. You will pay, if you consume much, you will pay approximately 1/10 of the tariff. You're now taking reactive power from the network.
Yes.
Opposite. Opposite will be this one.
It's going to negative.
Yeah. Active stands still, and reactive flows back. You will be fine here in our system for supplying reactive energy to network. Here, power factor is -1
But this one is
still, because no reactive energy consuming or supplied. You only send active to the network. Here. You supply active.
yes.
1 second, I will send for something like 0.7. Yeah. Now they are in half. Not in half. Angle is 45 degrees, but they are power factor is 0.7. Not in half. In half will be this 0.5.
But they are supplying.
Supplying and supplying reactive.
Yes.
Both go to the net. Consume active, supply reactive. Consume both. And here is opposite. You see? You supply active
Yes.
and consume reactive.
Reactive. Yes.
You take reactive from the net. It's a what it will be second quadrant. It's like this. You have mode plus Q minus P. It's It's this one. You send active to the network, but in the same way you take reactive from the network. Plus we consume. And you see methods go in opposite direction. Okay. Now where we are, minus Q plus P.
Yes.
Capacitive load. We send reactive to the net and we take active from the net. What can be done? It's 2 ohm meter. I should write somewhere how to connect. I always forgot. I connect them once once per year, and every year got how to add the second one. Goes in opposite. Both go in opposite direction. Is it visible? Goes. Active minus and reactive also minus. Yeah. Minus P minus Q. Yeah. Overexcited generator. We supply reactive to the net and we supply active to the net. They should pay us. Possible. Okay, you saw it. I think it was the first and the last time. 100% sure no one runs this demonstration. Now everything is about a PowerPoint and YouTube videos. Okay, I think it's enough for today. Or we need more questions? Remember this diagram. It sometimes pays. When you see bills from the power company. I think it's. I can stop this. Dying minutes.